if I have a change in the electric flux. Chapter 24.
Electromagnetically.
Yes. So if I have a change in my electric field, I got a change in the electric flux, which creates a magnetic field. If that magnetic field changes, I have a change in the magnetic flux, which creates an electric field. I basically get electromagnetic waves. So if I have a nucleus here, and I got electrons floating around, well, let's think about the orbital model of it. Just that's sort of that's coming, not right there yet. If I have an electron that's zipping around like this, the electric field is changing. If I look at it from this point of view, that the electron is moving up and down like that in a sine or cosine fashion. I can look at it from any direction, and that the electric field is changing like a trig function. Which means that as the electron is zipping around the nucleus, it should be giving off radiation. What should happen to the electron then if it's giving off radiation?
Should burn.
Should what?
Burn.
Burn? No, not burn.
I was going to say like bounce off of itself. Like if we just talked about how they bounce off of each other.
So the radiation would hit another electron. Let's simplify it. Let's assume that the radiation, ignoring the radiation hitting another electron in the atom. What's happening when something gives off radiation?
Gives off heat.
Okay?
Loses energy.
Yeah. So if I have an electron orbiting the nucleus and it's constantly giving off energy, what would happen to it?
Eventually it would lose all its energy.
And
Stop moving.
More specific than that here. Pardon?
Disappear.
Where?
It
Into nothingness?
Decay.
The electron itself would not decay in classical physics.
The nucleus would decay? Like the whole thing?
No, but we've called the key words of it said at this point.
The electron would fly away because.
Oh, the opposite.
It would like collapse itself?
Collapse.
Like go
It'd be
instead-
drawn to the nucleus.
Yeah.
Yeah.
That's onto itself.
As the electron is in a stable orbit, let's just assume it's in a stable orbit. If it's giving off energy, eventually it would just start spiraling in.
What happens when it hits the nucleus? Bad things happen?
It would get absorbed into it. Let's see. It probably would just be an electron in a proton suit.
No explosions?
Well, I think we all know no explosion. No, sorry.
Just checking.
Well, we know the electrons don't do that. All you have to do is in wintertime, drag your feet across a carpet and then touch a doorknob. You know the electrons haven't all collapsed into the nucleus. We can still scrape them off the outer part. Classical physics predicts that the electrons would go spiraling into the nucleus. So, obviously, not happening, so we got to do something about that. I'm going to take you through a couple of historical moments before we get into the solution for this. Historical moment number one, J.J. Thomson, discoverer of the electron, had this model of the atom, which is known as the plum pudding model.
The what?
Plum pudding model.
Okay.
Because apparently, he was British. Apparently plum pudding is, I'm guessing, a pudding based on plums, but there are raisins in it. And so plum pudding model is you've got this kind of this gooey mess here with raisins sprinkled throughout. And so he pictured that the atom was basically, you've got this sea of positive charges with electrons sprinkled throughout like raisins.
That does sound like British food. Plum and raisins.
Why not? And it might be good, I don't know. The word pudding puts me off, but other than that, that's good stuff. Now, if the plum pudding model is right, we've got these tiny little things, these very small particles in this mush. So what would happen if I sent something massive at it, what would be known as an alpha particle at the time, and what we now know is the helium nucleus. Helium nucleus.
Is that the only alpha particle?
Yeah, they call them alpha particles, and later figured out it's the helium nucleus.
Okay.
There are three main types of radiation. There's alpha radiation, which is helium nuclei. There's beta radiation, which is just turns out to be electrons, and then gamma radiation, which is the electromagnetic stuff that we now typically think of as radiation. So what happens if I took a helium nucleus? So we've got, in essence, 4 nucleons, 4 things like the size of a proton, being shot at this target. What do you think is going to happen to the helium nucleus?
So they're going to be pulled or pushed towards it? I'm thinking it from the charges point of view.
There would be some, well, actually, this would be neutral.
Oh, okay.
It would get destroyed.
Is this the bomb?
All right, so imagine you had a tissue paper and you shot a cannonball at it.
Oh, it punches a hole through it.
Yeah. So if the plum pudding model were accurate, you shoot this thing through it, and there might be some deflection because there's stuff in there. It should slow down a little bit because it's going through this quagmire of pudding. But for the most part, it's not really going to deviate much. Rutherford, probably, I would say, the greatest physicist who was eligible for a Nobel Prize in Physics but never got one. They ended up giving it to him for chemistry. Rutherford, famed for saying, all science is physics or stamp collecting. Anyway, 9 of Rutherford's grad students ended up getting Nobel Prizes. Anyway, so you shoot the helium, the alpha particle at the atom. And what he noticed is that he basically was using gold foil, shooting the alpha particles, helium nuclei at gold foil, and plum pudding model was right, almost everything would come up here. But sometimes, what would happen is he would shoot it at the gold foil, and it would bounce backwards. And he thought, wow, that's really not what's expected.
How does one shoot one helium particle?
I suspect they've got, you take helium, expose it to an electric field strong enough to rip the electrons off of it, so you just have the nucleus left, and then they all hate each other, then you can somehow project them. So once I have all my positive charges here, I have this positively charged, I have a plate over here that's negatively charged, so it's being pulled that way, but I have a hole so that
So is the hole only big enough for one particle? Or do you think they're?
I suspect that they shot a whole bunch of it. I don't know if they had the technology at that point to do one at a time. Eventually they would get that technology.
Is that what the big circle things are?
The cyclotrons? Like at CERN and Fermilab?
Possibly.
The big circle things like the size of several city blocks?
Yeah.
That's not for a single particle. You get millions of protons or whatever you're having, like firing, getting it close to the speed of light. Closer it gets to the speed of light, the more mass it has, and then you slam it into something.
But that's still a bunch of particles.
That's still a bunch of particles. So he shot the helium nucleus at the gold foil, some of them bounce backwards. Now, the way that you do this is you have a detector here. You have a detector here, and the stuff comes through, and you count the number of things that are coming in. Now, some of it is known as a scintillation chamber, so you're basically looking through this viewer, and you see basically when the helium nucleus hits the target, you'll get a tiny little light. Scintillation means a flash. And you look at that, and then you move to another spot, and you count the number that hit, and then you move to another spot, you count the number, and you get some distribution. And then you just keep going all the way around. One of the guys who actually did this, who was in the lab looking at this stuff, you know his name, did not get a Nobel Prize, but probably one of the more famous physicists, Geiger. I assume you're familiar with the Geiger counter. I can imagine if you were in a room trying to count the number of times something flashes, you would be inspired to come up with a different way of counting radiation or anything that's coming out.
So with this experiment, they were shooting these helium particles. Would there actually be holes in the gold foil? Or would they just...
I've never pictured that there are holes in it. I don't.
They just had a way to measure if it went through or not.
Wait, ask that again?
They just had a way to find out if the particle went through the tinfoil or went the other way?
Yeah, that was the detector that they had set up here that they moved around.
It was past 9:30.
Right. We got a couple minutes here. So the conclusion was that plum pudding model is not valid, and that each atom has a hard nucleus in it. And what's happening is you take gold nucleus, and we don't have a periodic table in here, but a gold nucleus is considerably bigger than the helium nucleus. Helium nucleus gets close enough to it, gets bounced backwards. And so through various measurements, you figure out what the size of the nucleus is, and you get the Rutherford atom.
So the times it was bouncing back was just that happened chance that it was hitting the nucleus?
Yes.
Of the gold?
Yeah. Because most of the time you shoot a bowling ball at a tissue paper, the bowling ball or cannonball is going to go through it. But occasionally,
There's a concrete wall behind it.
yeah.
How thin was the sheet?
The gold foil I saw, thin aluminum foil.
One helium atom is big enough to break through that?
Well, most of an atom is empty space. I mean, if you think of a ballpark, the nucleus would be like the size of an orange on the pitcher's mound. And the rest of it are I'll call it for now empty space with these tiny little electrons floating around it. In reality, there's electromagnetic radiation shooting all over the place. All right, so this gets us the idea of the nucleus, and from the nucleus, we now can make the prediction that the electron should spiral into the middle, which doesn't happen, so therefore there must be something else in here involved, and this enters in one of Rutherford's grad students, Niels Bohr. One of two father-son pairs to win a Nobel Prize. Niels Bohr and his son Aj both won Nobel Prizes in physics, doing separate things. The other ones were, let's say Thomson and Thomson. There was a father-son pair that worked together, and the father, I think the general belief is the father shared the credit with the son, but not sure how much the son actually contributed.
If you're that kid, no pressure, I guess.
Yeah.
Your dad gets a Nobel Prize.
I once,
And then the son of the second one who got the Nobel Prize.
I heard a lecture by Marie Curie's granddaughter, who has a PhD in chemistry, accomplished in her own rights. But just imagine Your grandmother won a Nobel Prize. Your mother won a Nobel Prize. And all you got to show for it is a PhD? Come on.
Get it together.
All right, we're gonna end it here. There were some people who owe me some stuff, like the quiz yesterday. So, we will assume the lab is done.
That was a lot.
Because another class, once the room just goes